I will discuss now extra example number 1. We're given two objects of equal masses hang in equilibrium from two strings as shown, which I will draw now. Here's one object of mass m, another object of mass m. That's how they hang. The upper string is cut. Immediately after that, what is the acceleration of the upper mass? This one. There could be a tendency to say, oh, now that the spring is cut, so this will fall freely, and its acceleration will be g, 9.8. That would be too hasty of an answer. Let us try to analyze this problem carefully. Before we cut the spring, what forces act on the masses? If I draw a free body diagram for the lower mass, what do I have? I have mg down. I have the tension up. Let's call this tension T1 here. I have the tension T1 up. Now, since the mass hangs in equilibrium, the net force on it is 0. So, before cutting, T1 is equal to mg. So I have here T1, here mg, those are equal. How about the upper mass? The upper mass, if I draw a free body diagram for the upper mass, I have mg down first. And then I have T1 also down, which is equal to mg. And I have T2 here, let's go T2, the tension here, T2 up. So T2 must be equal to twice mg. T1 is mg, and another mg, so I have 2 mg down, T2 is 2 mg. So T2 would be 2 mg. This is a situation before cutting. Now we cut the string, the upper one. When I cut this, what do I have? I can ask what forces now act on the upper mass. Once I cut this, then the tension is gone here. So T2 now is gone. But still, immediately after the cutting, now there's the tension here, there's a tension here, T1, and there is mg. So immediately after cutting the upper string, the net force F net on upper object is what? T1 plus mg. But T1 is mg, so it's equal to 2 mg. So what is the acceleration? F net divided by m is equal to 2g. So it's 19.6 meter per second squared. So immediately after you cut the string, the upper object moves down with twice the acceleration due to gravity. It moves down with acceleration 2g.